Welcome. Today we will be seeing about working principle of a DC machine. This is the generator. Okay, this generator has a permanent magnet of North Pole and South Pole, and this is the coil ABCD, which is present inside the magnetic flux from the North Pole to South Pole. And from the coil ABCD, two terminals are taken out, and these two terminals are connected to the slip rings. Here, A and B are the slip rings, and the terminals 1 and 2 are the brushes, and from these two brushes the load resistance is connected, and this load resistance is R, and the two terminals are M and L. Okay, here what they have done is they have rotated the figure and given to you. Both are same figures. Okay, imagine the coil ABCD to be rotating in clockwise direction. Okay, so this coil ABCD, which is present here, is being rotated in a clockwise direction. As the coil rotates in the permanent magnetic field, the flux linked with it changes. You know that if the coil is moving inside the magnetic field, at once the magnetic field which is linking the coil get changes because the coil is under motion because it is rotating in clockwise direction. So the flux linkage will change. Due to change in flux linkage, an EMF E is induced in it. So since the flux linkage is present in the coil, according to Faraday's law, what happens here is in this coil an EMF is induced in it. This induced EMF is proportional to the rate of change of flux linkage. So the total quantity or the total amount of EMF which is produced in this coil will be equivalent to N into T pi dt. Here the N represents the number of turns present in the coil, and the pi d pi term represents the total amount of flux linkage in the coil, and dt, this term represents time taken for the rotation. Okay, so the total induced EMF produced due to flux linkage is E, and which is equivalent to N d pi dt. Here, when you see this figure, this is the same figure as shown above. This is the north and south permanent magnets, and this is the coil. You can see the coil very clearly, A, B, C, and D, and this is rotating in clockwise direction. So you can see in position 1, the coil is right angle to the line of flux. If you see here, the flux lines are passing like this, and the coil is in position 1. At this position, the flux lines are right angle to the coil. So the flux linked with coil is maximum, but rate of change of flux linkage is minimum. Since the coil is in position 1, say theta is equal to 0 degree, at this point what happens here is the flux link with the coil is maximum because it is in 90-degree position, but the rate of change of flux linking is very minimum. So what you get here is the coil sides AB and CD do not cut the flux, rather they slide along them. You can see this is the flux line. All the green arrows are represented here. These are the flux lines, and the plane of the coil sides AB and CD do not cut the flux, rather they slide along them. You can see the sides AB and CD are present here, and these are the flux, and these flux lines will passing through the coil like this, so that the flux line will not cut the coil AB and CD. It will be parallelly passing through the coils. So the induced EMF is zero. As coil continues to rotate, the rate of change of flux linkage increases. So at this position 1, you can see this is the position 1, and here the coil is in 0 degree. At this position, you can see the rate of change of flux is minimum, so that the voltage produced is 0. Similarly, when position 3 is reached, say when theta is equal to 90 degree, now coil plane is horizontal. So now you can say that the coil AB and CD has been rotated, and now it reaches the position 3. At this position, the coil is parallel to the lines of flux. Now the lines of flux will be parallel with the coil AB and CD. At this position, the rate of flux linkage is maximum. So due to maximum fluxes cutting in the coil, you will get a peak voltage at the third position. Flux linked with the coil is minimum, but rate of change of flux linkage is maximum. So the maximum change of flux which is present in this coil creates a maximum positive peak voltage. So maximum positive EMF is induced in the coil when in this position 3. Okay. In the next quarter revolution from 90 degree to 180 degree, flux linked with the coil gradually increases. Here you can see from 90 degree to 180 degree, the flux linkage, that is from 3 to 5. Okay, from third position to fifth position, what happening here is the flux linked with the coil gradually increases, but the rate of change of flux linkages decreases. So due to the decrease in rate of change of flux, what happens here is after this peak voltage, due to decrease in rate of change of flux, the voltage starts to decrease. Hence, the induced EMF, that is this voltage, starts to decrease. In position 5 of the coil, it is reduced to a zero value. So at this position, the EMF will become zero, so that the induced EMF is zero. The direction of induced EMF is found by Fleming's right hand rule. So, if you make a Fleming's right hand rule, at once the direction of induced EMF can be found. Hence, the direction of current flow is along AB, ML, CD. So, here you can see the current will flow from AB and through the resistance ML and again back to C and D. The current through the load resistance R flows from M to L during the first half revolution of the coil. So during the positive half cycle of the sinusoidal waveform, the current through the load resistance will flow from M to L. In the next half revolution, that is from 180 degree to 360 degree, variation in magnitude of EMF are similar to those in the first half revolution. So when you consider from 180 degree back to 360 degree, the variation in the magnitude is same, but what happens is the direction, that is the magnitude sign, here it is in positive value, but the next from 180 to 360 degree, the sign of the induced EMF gets changed. Here you will get a negative sinusoidal waveform, and here is the negative peak of the sinusoidal waveform is produced. Voltage is maximum when the coil is in position 7 and minimum in position 1. So when you say when the coil is in 270 degree at this position, you will get a maximum negative peak voltage at position 7. Similarly, at position 1, here the ninth position is same as first position. So at position 1, you will get a zero value back. But it is found the direction of induced current from D to C and B to A. So now the current which is flowing through the external resistance gets reversed and it starts flowing from D to C and B to A. The path of current flowing is along DC LM BA. Here the current will flow from DC LM, which is external resistance, and through B and A. This is just the reverse of previous direction of flow. So you can compare. In the first direction of flow, the current is flowing from ABMLCD. In the second direction of flow, that is DCLMBA. So, for the positive half cycle, the current is flowing in the direction of ABMLCD, and in the negative half cycle, the current is flowing across DCLMBA. Current, which we obtain from a simple generator, reverses its direction after every half revolution. Alternating current not only reverses its direction and does not keep its magnitude constant. So you can see here the current direction is reversed for each magnitude change. In a positive cycle and negative cycle, the direction of current is changing from ABMLCD, and for the negative it is from DCLMBA. For making flow of current unidirectional in external circuit, slip rings are replaced by split rings. Here, to convert this current in bidirectional current into a unidirectional current, we need to convert the current by replacing slip rings into split rings. Here, this is known as split rings. Okay, split rings are made out of conducting cylinder, which is cut into two halves or segments insulated from each other by a thin sheet of mica. Here, this cylinder is a copper cylinder, and in the center position is cut into two halves, and this one is a mica. Okay, and here this is the A portion and the B portion of the split ring, and these are the two copper brushes, 1 and 2. This is the copper brush 1 and this is the brush 2. Okay, these brushes are made up of carbon as well as copper. This is the complete diagram of a DC machine or a DC generator. You can see the slip ring is being converted into split ring over here. Here you can see the segments AB and the external resistance ML and the coils as well. For the first half revolution, current flows from AB, ML, CD. Here you can check the current starts flowing from AB and through ML and through CD back. Okay. Now the brush number 1 in segment A acts as positive end of the supply and B as negative end. Here this is the segment A and this one is the segment B, and here is the brush 1 and here is the brush 2. Since the current is flowing from A to B in this direction, here the current enters from M to L. So you can see the segment A is positive and the segment B is negative, whereas the resistance M is positive and L is negative. Okay. Hence, the current in the load resistance flows from M to L. Okay, the current flows from M to L. In the next half of revolution, the direction of induced EMF or the induced current in the coil has reversed from DCLMBA. Okay, now the induced current starts to reverse and it will move from DCLMBA. At the same time, the positions of the segment A and B have also reversed. You can see here, this is the previous diagram. Here the current is from AB, ML and CD. Okay, here the segment A is positive and the segment B is negative. But after the one half rotation, you can see the current starts to flowing from DC, BML, BA. Okay, what happens here is now the segment B becomes positive and the segment A becomes negative. When comparing this figure, you can see the segment A is having a split ring. What happens here is the segment B remains positive, becomes positive, and the segment A is negative, so that the brush 1 remains positive and the brush 2 remains negative. Due to this, the resistance M and L, the current starts flows from M to L. You can see the brush number 1 in segment A acts as negative end of the supply and B as positive end of the supply. So how the current flows from ABMLCD or DCMLBA? In which direction it flows, the supply, that is the current, starts flowing from M to L. So a unidirectional current is being achieved with the help of split rings. Hence, the current and the load resistance again flow from M to L. So, on comparing these two figures, you can see the current is flowing in the same direction as M to L. In this figure also, it is in M to L direction with irrespective of coil rotation from 180 to 360 degree or 0 to 180 degree. This current is unidirectional but not continuous like pure direct current. You can see the waveform which is measured across M to L. Here the current is unidirectional but it is not continuous. It is having a dip after every 180 degree. Thank you.